Hey Tech Math, here are the guided notes for 10.6. We're going to be talking about normal distributions. I love normal distributions. I think that they can be a little bit confusing at first. However, once you get to see the patterns that exist within them, they are really, really interesting and they're very useful for real life. So if we just look at this top part, normal distributions intro. Suppose your job is to test the life expectancy of a certain brand of tires. You tested 96 sets and found the results in the table below. If you put them into a graph, you can visualize that information. So if you look at this graph and at this table, the table doesn't tell us a ton, but when you look at the graph, what you're going to notice is a shape. And this shape gets smaller at the ends and larger or taller at the middle. This shape is what we're going to be talking about. This is called a normal distribution, and it's in the form of a bell curve. You'll notice it looks kind of like the old-timey church bells. Now, why is this pattern so important? Well, if we think about tires, what this graph shows us is that there's going to be tires that don't last very long. That's going to be a pretty small little bunch over here. And we're going to have some tires that last a really, really long time. But again, that's a really small bunch over here. The majority of tires are going to end up somewhere in the middle here, lasting a medium amount of time. And you're going to see that for a lot of different real-world examples. So a few things about normal distributions. The first thing I want you to know is that the mean, or the average, the median, and the mode are all the same. And they all end up right in the middle of the graph. So your average is right here, your mode is going to be right here, and your median is obviously going to be right there because they all end up in the center of your graph. The second thing I want you to know is that a normal curve, a normal distribution, always has a bell curve. And that's the curve that I just showed you up here. It's also the curve you see below you. Now, examples of non-bell curves, that's going to be things that are skewed one way that end up having a really long tail. They look like a wave. That's not a bell curve. Things that are straight up and straight down, not a bell curve. Things that maybe look like they're going to be a bell curve but then have a dip in the middle, not a bell curve. It has to be this nice smooth shape. Once we have a bell curve, the really cool thing is they're easy to look at. So if you look at this, we know that our mean is always going to be in the middle. And I'm going to introduce a symbol to you that's called mu. This little symbol tells us that that is the mean. And I'm going to put that right in the middle. So right in the middle of our graph is our mean. Makes sense because we know that the mean, the median, and the mode are all the same. Next, we talked about standard deviation in our lesson yesterday. This is where that information is going to come back into play. Each of these little tick marks on either side of the mean are called standard deviations. I'm going to introduce another symbol to you that's called sigma, and that stands for a standard deviation. So if you are 1 sigma above the mean, you are 1 standard deviation above the mean. You can also be -1 sigma. That means you are below the mean. We can also have 2 sigma, and way over here at the end, 3 sigma. And then, of course, they go in the other direction as well. Now, the standard deviations aren't super important here, but what they mean is really important. So if you look at this graph, and I think about putting 100 data points on this curve somewhere in here there's 100 data points. I know that within 1 standard deviation, there's going to be 68% of my data. So, from negative sigma all the way over to positive sigma, I'm going to put a positive there, that's 68% of my data. From -2 sigma all the way up to +2 sigma, I'm not only going to include the 68% of data that falls here, I'm also going to include the next set of dots. And you're going to find, when we look at statistics, that 95% of data falls within 2 standard deviations. That means out of your friend group, 68% are going to be pretty average. 97% are going to be a little bit taller, a little bit shorter than average. And you're going to have very few people falling in the -3 to +3 range, outside of that range. Excuse me. But 99% of your data is going to be here. Now, what happened to that last 1% of data? Because it looks like our lines stop here. Well, let's think about it. There's always the Shaquille O'Neals and, the Kobe Bryants of this world who are way, way over here and they're super, super tall. You're always going to have outliers. But it doesn't mean that 99% of your data will still fall within this area. And these are the numbers I'm going to want you to use and remember. So these are really important. I would write these down. So let's now look at some examples of how we use all of that information that I just threw at you. Well, if I give you this distribution of carrots and cucumbers that you grew in your garden, if we look at carrots, that's going to be this one right here. I know it's harder to see, but I'll do some color coding for you. Carrots, we look and we see that the mean falls at right about 5. So we know that the middle of our normal distribution is always our mean. So if it asks me for a mean, I know that that's about 5. Now, standard distribution's a little bit harder to see on these graphs, but I usually try to make a solid estimate. If I know that my 2 ends of my graph are at about 0 and 10, for carrots anyway, that means that 99% of my data is going to fall in between there. If I have 6 chunks here, I have 2, 4, 6 chunks split up between both ends, what I'm going to end up doing is I'm going to say 10 divided by those 6 chunks. This tells me that a standard deviation is going to be about 1.6. That says that each standard deviation strip, each one of these, is going to be about 1.6 or 1.7 units long. So that's what we're going to go with. We're going to say the standard deviation is about 1.7. Now for cucumbers, let's use a different color here. See if I can get a red maybe. There we go. If I drop my line down in the dead center, it's a little bit hard to see, but I'm going to estimate that that is probably right in the middle of 5 and 10. I'm going to say it's probably about 7.5. I'm going to do the same thing with my standard deviation. I see it starts at about 0, but it ends up at about 15. So I'm going to take my 15, my total standard normal curve, divide it by 6. This tells me that each section of my standard deviation is probably going to be about 2.5. So if general standard deviation is going to be about 2.5. So that is how to look at a graph and figure out those points. Let's jump over to the back of the notes now, because we may not be given a picture. Ignore my ink blot here. We may just be given some information, and we may have to find out the mean and the standard deviation. So this says that 95% of students at school weigh between 62 kilograms and 90 kilograms. Assuming this data is normally distributed, that's very important. That tells us the bell curve is involved. Bell curve. What are the mean and standard deviation? Well, if I throw a quick bell curve here, I know it's not going to be perfect. I know that my average is in the middle. I know I've got 1 standard deviation, and then I've got 2 standard deviations. And it says that if 95% or 2 standard deviations fall between 62 and 90, What that tells me is that my 62 is going to be my lower second standard deviation, and 90 is going to be my upper standard deviation. So then I have to use that information to find the mean and to find what a single sigma or standard deviation is. Now, yesterday we learned how to find standard deviation when we had a ton of data points, and we could just calculate that right out and get our answer. Today we don't have that, we only have the information from this graph. So how are we going to find it? Well, if we know that these are evenly spaced, we know that mu has to be right in between them. So what I'm going to do is I'm going to say to find the average, I'm going to take 90 minus 62. That's 28. That means there's 28 units in between here. If I want to find what's dead center, I just divide by 2. So that is going to be what one of these sections is. Like one of these sections is. So if I want to get right to the middle, I'm going to find what's right in the middle of these two, and it's going to end up being 76. The other way you can do this, I should have done an adding here, because this shows me what's right in between them, 76. You could also count and figure it out that way, but I personally prefer to just add them and divide by 2. So now how do we find out how to find the sigma? How do we find a standard deviation? Well, we just found out that between 60 and 90, there's 28 units. And we want to find what each one of these 4 chunks ends up being. Well, if I divide the 28 that's in between 62 and 90, there's 4 chunks total, making each chunk worth about 7. So I now know that mu is equal to 76, that's my average, and a single standard deviation is 7. This tells me that the average student at this high school is 76 kilograms, and it is, to be 1 standard deviation off, you'd have to be about 7 kilograms heavier or lighter to fall within 1 standard deviation. All right, that was a little confusing. I got my notes a little mixed up, so let's look at another one. A machine produces electrical components. If 99.7, we're gonna round that up to the 99, of the components have lengths between those two numbers. If we assume it's normally distributed, what are the mean and standard deviations? Again, we're gonna throw up a bell curve, and it says 99.7. So that puts us all the way out. If we remember from here, 99.7 or 99% of our data falls between the -3 and the +3. So we have to click out 1, 2, 3, 1, 2, 3 in both directions. And this will be associated with our lower 3, 1.176. And this will be associated with our upper 3, so 1.224. If we want to find the average of a component length, we need to find what's right in between them. So this is where we took last time. We said 1.176 plus 1.224. We get 2.4. 1.224. And when we divide it by 2, we're going to figure out what's right in the dead center. In this case, 1.2 is our exact average. It averages out to a nice decimal. That's kind of fun. So I now know I can put 1.2 right in the middle. And that makes sense because it's larger than 1.176 and smaller than 1.224. To find sigma, I'm going to look at the distance between them. I'm going to say 1.224 minus 1.176, and I'm going to divide by the number of sections in between. So there's 1 section, 2 section, 3 section, 4, 5, 6. Since there are 6 total sections, I have to divide by the 6 standard deviations that are in there. And when I do this, 1.224 minus 1.176 divided by those 6 deviations, this one's going to be really, really small because there's not a big standard deviation here. We get that 1 deviation is about 0.008 centimeters. So not a very big change there. All right, let's see one more. 68% of the marks or scores on a test are between 51 and 64. What are the mean and standard deviation? Again, we're going to start by throwing up our bell curve. We know our mean is right in the middle. And if it says 68% of the data, we go back to our front page and we see that that is associated with 1 standard deviation. So we're going to go out 1 mark in each direction. And we know that the scores associated are 51 with the lower and 64 with the higher. So to find our average, we're going to find the dead center by saying 51 plus 64 divided by 2, because that's in the dead center. 51 plus 64 divided by 2. We get exactly 57.5. You can put that on your graph if you want to. I'm not super worried about it. If we want to find sigma, then we have to find the difference and say 64 minus 51 divided by 1 section, 2 section. When we do that, 64 minus 51 divided by 2, we get that 1 standard deviation is 6.5. So this means that the average on this test was a 57.5, and that the standard deviation, so a student who did significantly better, was about 6.5 points higher than the average score. So there are your notes for 10.6. Standard deviations and normal curves can be a little confusing, but if you just remember to follow your formulas where you add and divide by 2 and then subtract and divide by the number of standard deviations, you should be good to go. Let me know if you have any questions.